Well, I'm very excited about this next session. Uh, we we have with us, this is a very rare event to have this many assistant directors of the National Science Foundation attending something like this. Probably would not be possible if we had relied on them all physically being here. In fact, I can almost be sure it wouldn't be possible. So, hello? Okay, you hear me. So, the term cyber infrastructure, you know, was coined in the context of NSF. I had the privilege of chairing a blue ribbon panel that created a major report which helped launch this initiative at NSF and helped articulate new opportunities that cyber infrastructure presented for research and learning, particularly in science and engineering, although it's now widely affecting the humanities and the arts and so forth. And in fact, on Friday, we will have the international meeting of the Haystack community, which is the preeminent community around digital humanities. So it's had a broad impact. And then I was asked to launch an Office of Cyber Infrastructure at NSF, which I did. And now, you know, we have a group of people here who are in a position to give you an update on what's happening in the context of NSF and where things are headed with cyber infrastructure and naval science, both from the perspective of creating it, of education associated with it, and from scientific application now in almost every field that NSF supports. So it's my great pleasure to have here Alan Blatecki. Alan, if you could raise your hand, who is now the director of the Office of Cyber Infrastructure, which I helped launch at NSF, and has an extensive experience. There is a brief bio of all of these people in the website. And then, as I said, this is not just applicable to research, it's applicable to learning. The term cyber learning is now being widely used within NSF, and it's setting examples which are being taken up by other agencies. And that is occurring within the Division of Educational Human Resources in conjunction with other directorates. And we have with us Joan Farini-Mundi, who is the director of, head of the Directorate for Education. Joan, if you could raise your hand. I think you're pretty obvious in that group. Myron Gutman is one of the several who have ties to the University of Michigan, who is doing a tour at NSF, as well known to many of us here from the ICPSR. Myron is sitting right next to Joan in the middle. Farnham Johanian, where is Farnham?
He's off on the right.
Up on the right, there he is also extremely well known. He's also doing a tour. One of the themes of this presentation is how benevolent NSF, or the University of Michigan is being and allowing its best people to go help the nation through NSF. And then Tim Killeen is head of the geosciences. I should say Farnham is head of the Computer Information Science and Engineering Directorate. Tim Killeen, it's most recently been the head of UCAR, of NCAR, but has ties to Michigan, was a distinguished faculty member here, was an associate vice president of research, and is now the head of the geosciences area. And then Ed Seidel, sitting in the front, as far as I know, it doesn't have Michigan ties, but
Sorry.
But is someone that I played a role in recruiting to head of the Office of Cyber Infrastructure, but then due to a sudden departure of the head of math physical sciences, he was recruited into that. So he now is directorate of the overall, but is well known probably to many of you for his computational work, particularly in relativity and so forth. So we have an amazing team, both personally and from the perspective, from their administrative perspective right now. And I've asked each of them to take not more than 10 minutes to give you a perspective on cyber infrastructure, broadly defined in the context of their particular field for which they're responsible. So,
We'll have time for questions at the end.
and we'll have some time for questions in the end. So why don't we just do this in the order I have them? We'll let Alan go first, then Joan, then Myron, Farnham, Pim, and Ed. Okay? So Myron, or Alan?
Okay, can you hear me all right?
We can.
Yeah, great.
Okay. I'm just going to take a few minutes. I'll do a couple of things. I want to talk a little bit about a project, an effort we have here at NSF called the Cyber Infrastructure Framework for the 21st Century, and then a little bit about, I think, how that might apply to the campus, actually. But let me start with the first general statement, and I want to make sure people understand when we talk about cyber infrastructure, we're talking about an ecosystem. Too often we think of cyber as being just computing or networking or technology, but it also involves organizations, it involves expertise, instruments, data, software. All these things have to work together in a coordinated fashion in order to work. So that's sort of the first point. The second thing I just want to mention is that a lot of the stuff we're doing today, looking at cyber infrastructure and science, is being driven and transformed by data. Data is impacting our lives and society throughout science. We're looking at very complex data products coming at us. We're looking at multidisciplinary teams to solve the challenges of the next aspects of research and science. And we're really awash in the sea of data, also often called a tsunami of data. And let me do one more level setting thing. Then I want to talk specifically about, I think, what we're doing here. When we often talk about data, there's a whole range of things we need to talk about here. One is what I talk about in terms of volume of data. Today, we're looking at often gigabits and terabits of information. In 5 to 10 years, that'll become petabytes and exabytes. So one issue we have to look at is the sheer size of volume of data itself. The second part of this same thing is you're seeing more and more instruments coming online. So, for example, you're seeing sensor networks generating tons of data. You're seeing genomic sequencers on the campus generating tons of information. So you've got more and more instruments generating more and more data. So it's growing at an exponential rate. The next component is that we often don't pay attention to is we need to think in terms of data in terms of 10, 15, 20, 30, 40, 50-year timelines. Often we tend to think of data as something we just do now and they have it here, but what about sustainability? Is it going to be there 20 years from now or 50 or 100 years from now? And if we're basing our research on it, we have to have it available. So there's an issue that is coming loud and centered to all of our discussions. The third component I want to talk about is distribution. If you're looking in some cases, data centers are located in a few places. You've got a lot of data in one place. And for example, scientific instruments such as colliders or telescopes may indeed put their data in one or two places. And that's one set of issues. When you look at things like genomic data or you look at climate data, you're looking at literally thousands of locations of data. And so the issue here is the distribution is quite different. How you manage it, how you communicate with it, take advantage of it, is a very different set of issues and much more complex. And of course, the fourth point here is without having adequate data access to any of this, it's all meaningless. So one of the issues we have to look at is, do you have access? There's speed issues, there's policy issues, there's all sort of other things going with it that we have to look at. And the fifth component I want to mention is just when we look at sensor networks and data in general, there's sort of two flavors of that. One is where you may get data on, let's say, an annual basis or weekly basis, but you may have data that is real time, in which you're concerned now about literally microsecond or nanosecond capabilities. Again, two different ways of looking at data. So that's sort of the background, and the point of all this is we're using this whole sea of data to address grand challenges and solve science issues. And so what happens in this situation is you're looking at data, you need software, you need expertise, you need algorithm development, all these things to take advantage of that. So what we've done here at NSF with CIF 21 is what I'm calling a cyber infrastructure inversion. And the point here is, let's base the activity on science. What does the science base needs for the work we want to do? What are the grand challenges we're looking at? Asking directorates, if you will, to provide leadership and saying, here's the science that needs to be done. And cyber then becomes a tool to help make that happen. And from our perspective here, OCI then becomes a partner in helping to enable that partnership to take place and to create the new science. A couple of components I'd like to mention. One of the aspects of this is it's almost always multidisciplinary. We've got multiple folks involved. The second thing I'd like to point out is this is also multi-year. Cyber infrastructure is evolving quickly, but we still got a long ways to go. So you need to think in terms of a multi-year activity, and comes with that then the whole idea of spiral development, which means that You may do something this year, next year you may look at it again and say, you know, we need to tweak it and go this direction, or here's a new capability we need to bring in. So you continually evolve capabilities as you move forward. So what I'd like to suggest is, I think that's a model I think that campuses can also take advantage of. So I'd just like to sort of close with a couple of principles I think you might want to think about. One is, you know, to identify science and education challenges on the campus. What are the key ones you want to address? If you've got those in place, then you can step back and say, what are some common approaches we can use to solve some of these? One of the problems you often run into cyber infrastructure is you build a solution just for a particular application. And it really becomes important to say, how do we not build multiple silos doing the same thing? So how do we look at common approaches across these activities? And if you identify a challenge up front and ask those questions and keep your system architecture open, it'll really help. The other one I'd just like to mention is one of the things that's really important is we talked about using organizations and people involved in here. So it's really important to look at some sort of shared governance. How do people have input into what you're doing and be able to say, how about looking at this? How about changing direction? How about looking at a new capability and bringing it in? So how do you involve the users, if you will, as drivers and owners and directors of the activities? This, I think, is a key component to make it work. And again, the whole point of this is this has to be done in the long term, but do in mind, and ability to say, look at inner milestones, and capabilities to move forward. So let me just stop there, and I guess we'll go through and then have questions at the end.
Okay, thank you. Joan?
Yes, hi, Dan and everyone. Can you hear me?
Yes.
Okay, great. So I appreciate the chance to be a part of this discussion today, and would like to just give a little bit of a perspective from the Directorate for Education and Human Resources. But I'd like to begin by pointing out that I think several of us in the room, all of us in the room, I would like to hope, and other colleagues across the building are quite excited by an emphasis that the new NSF director has asked us to really work on, which is kind of a reformulation of the notion of the integration of research and education, which of course is a cornerstone for NSF. But as we try to think about this going forward, we're translating it in a variety of ways, one of which is this notion that all of the investment across the agency in science research can be improved by a strong connection to ideas about education and about learning and about workforce development. And similarly, the investments that we make across the building in education and learning can be very much be informed by both the science research that goes on outside of EHR and the research about teaching and learning that goes on here. So this is a bit of context that I think helps set the stage, at least for how EHR is thinking about cyber infrastructure and cyber-enabled learning and cyber learning today. And there really are 4 areas of interest for EHR in this domain where I'm sure that folks in the room are aware of some of our programs, and we'll continue to make it clear that these are programs that invite cutting-edge work. But the 4 areas are as follows. One is the notion of actually exploring new research questions in STEM learning and teaching that are now possible to explore because of cyber infrastructure or because of cyber learning tools. We can get new glimpses into learners and teachers and into classrooms and have new capacity for compressing and analyzing and working with large data sets. So I'll say a bit more about that one in a moment. But the first question, as I say, is what new research questions about teaching and learning can we pursue? The second is what new and more effective tools and approaches to teaching and learning can be built, designed, and implemented, as well as studied. The third is our new expanded capacity to undertake secondary analysis of large data sets that bear upon education, that can give us more insights about teaching and learning with new methods and new tools. And then finally, the 4th area of interest for us is, and with our colleagues I'm sure, is the development of human capital. What does the workforce look like going forward as we think about the cyber infrastructure and the deluge of data, as well as cyber learning? What kinds of skills and talents are going to be needed, and how does NSF investment help to nurture those? So being a little bit more specific now, first on this matter of exploring new research questions in STEM learning and teaching. As you think about what's possible in classrooms today, and imagine the ways in which researchers and practitioners can work together to take good advantage of new tools, Think about the possibilities, for example, in tagging, coding, and analyzing video data now using more sophisticated techniques than the traditional methods that we have tended to use of very deliberate work by hand, to produce video analytics that can be used in real time to assist teachers in their day-to-day work in classrooms, for example. Or the role of visualization much more generally, and thinking about how learning of complex concepts in the sciences and mathematics areas might be facilitated by visualization that could be, again, facilitated by use of cyber infrastructure and cyber tools. And then finally, with intelligent tutors, we have new capacity to predict student behavior and to ask questions about student learning under certain kinds of conditions with certain sorts of supports and tools. And I think helping the fields of cognitive science, of STEM education research, computer science, mathematics, and others begin to work together to explore what new questions can be examined is a sort of interest that we would certainly like to encourage here in EHR. On the matter of new and more effective tools and approaches to teaching and learning, we have now possibilities and have funded work that allows for real-time assessments by classroom teachers using cyber tools, simulated classrooms, simulated students and learners for use in teacher professional learning, data available coming in from NSF-funded large facilities and centers that would allow for real-time data sets to be available in classroom settings, in undergraduate settings for student analysis, for student learning opportunities, figuring out how to take really good advantage of all of this in ways that will lead to improved learning. Again, that's a sort of question that we in EHR are quite interested in. On the matter of extended capacity to undertake secondary analysis of large data sets, something that the education field in the STEM areas has probably not taken as much advantage of as it might, and would perhaps over time require more involvement with those interested in cyber infrastructure and tools. When we think about the large international comparative studies like PISA, TIMSS, TEDS, or the national assessments like NAEP, we stand to learn a great deal more about student learning and about teaching by deeper examination of those data sets. And as state longitudinal data systems are becoming more and more available, particularly with the sorts of linking and integration that happens across multiple data sets, we can begin to better understand the impacts of teacher preparation programs, of students' trajectories across their educational experiences, even of the varied curricula that are used in schools as time goes on. And then other major studies, such as the Gates Foundation's Measures of Effective Teaching, that are amassing major collections of video. Being able to imagine how such collections can lead to secondary analysis that will tackle hard questions in teaching and learning, all very exciting for us. And then finally on human capital, because EHR is home to several of NSF's foundation-wide human capital development programs, like the Graduate Research Fellowship Program or the IGRT program. As we think about moving forward and imagining tomorrow's workforce in this space of cyber infrastructure, cyber learning, cyber tools, new characteristics perhaps become important and can be built into some of these workforce development programs, opportunities for working collaboratively in interdisciplinary teams, for learning to work with big data, even when folks' disciplinary backgrounds don't necessarily include that kind of preparation, how to build the right sorts of teams and so on. And how does this preparation for the workforce begin, and at what levels, and what might we even be doing to help to interest undergraduates in some of these territories as they prepare for graduate school. So EHR is excited to be a part of all of this, and look forward to our conversation.
Thank you very much. Thank you. Myron?
Okay. Thanks very much. This is fun to come home in a way to visit with my friends at Michigan. The SBE Sciences have a quite interesting and long history of cyber infrastructure and sharing of data. And those data and those opportunities overlap a lot with the things that Joan just was talking about. I'm pretty sure that the data from the Gates projects that you talked about are on their way to Michigan, for example, for archiving. It's interesting because from what we see, that there, cyber infrastructure for the SBE Sciences really brings together a combination of needs of hardware and software and people that are really fundamental to understanding the ecosystem that Alan described. For the most of its experience, the SBE Sciences have worked a lot with sharing fairly straightforward data sets about people and their behavior or their attitudes in the economy. But that's really moving and changing now quite a bit. I talk sometimes about 4 use cases for cyber infrastructure for the SBE Sciences. One, which is the most common in the past, has been the use of cyber infrastructure for analysis, either statistical analysis or data mining analysis of very large data sets, increasingly large data sets. A second is the use of cyber infrastructure for visualization. Again, these are very common themes from what you've heard and will hear from my colleagues. A third is increasing intention to simulation of human issues. And of course, a fourth is the creation of a response to grand challenges that cut across scientific domains with simulations and analyses that go across the earth sciences, the physical sciences, the biological sciences, and the human sciences. So there are lots of new opportunities within these use cases, and I'll mention 2 or 3. I mean, this all builds upon the long practice of having data about people, places, firms, and schools that need cyber infrastructure to bring them together, either because of their complexity or because of the need for linkage, to bring them together for analysis, and also to put them in an environment where information about people is protected because of risks to confidentiality and privacy. But there's much more than those classic issues. We increasingly have digitized collections of physical objects relating to people, be they bones or other artifacts that people have created that are now being made available in digital format, but we need cyber infrastructure to make sure that a researcher working at the Smithsonian not far from here who's working on a skeleton can compare that with what a researcher might have available at the Field Museum in Chicago or at the Natural History Museum in San Francisco. We have larger and larger compendia of linguistic and textual corpora that are offering enormous opportunities for linguistic and cultural analysis. We have the kinds of video records that Joan was talking about of human behavior in their context, whether it be schools or businesses or other places that require encoding and comparing and analysis. And finally, of course, very much at the heart of the technological revolution is we have this enormous and emerging collections of social media data, or actually just new technology data that are available, that are streaming by us, and that open up real opportunities for understanding human behavior. All of this exists in an environment where SBE science and its connections to other sciences allow us to try to identify grand challenge problems and find solutions for them. That we are mostly interested as a society in what we do as people, and the kinds of opportunities that SBE science has to solve some of those problems, or at least to advance answers forward, is really important. And therefore, it spans scientific domains and provides important solutions. Finally, SBE science has the opportunity to provide evaluation and design related to the cyber infrastructure itself. If we're going to understand how cyber infrastructure operates, how these new social media and connections are going to work together, it's the SBE sciences that are really critical for designing the way they work and for evaluating how they perform because of their inherently socio-technical nature. So there's a lot of opportunities for SBE science with cyber infrastructure and a lot of ways that NSF is working to understand that.
Thank you very much. Farnham?
Greetings to my friends and colleagues back at Michigan. Again, thanks for the opportunity to spend the next few minutes sharing with you some thoughts about what the SISE Directorate is doing and also our interest in cyber infrastructure. I think there's broad recognition that computing and communication is at the center of an ongoing societal transformation, and that's going to continue for several decades. Whether it's the explosive growth of scientific or social data, as Alan alluded to, or wireless connectivity at broadband scale, or access to resources in the cloud, there's no question that we're seeing a transformation in the way we play, we work, we learn, we communicate, we do various kinds of scientific exploration and discoveries. I think the expectation is that computing and communication is going to go deeper into sciences and engineering and will become much, much more pervasive. With that context, I think the opportunity, particularly for the computing and information, broadly speaking, community, is that it has the potential to form a pervasive intellectual fabric that connects a wide range of disciplines. And this is in recognition of the fact that scientific discovery and engineering breakthroughs are going to happen at the core of, are going to be at the core of our response to a number of challenges that face humanity and face the nation, but also many of these breakthroughs are going to happen at the intersection of various disciplines. And my expectation is that, our expectation is that computing will play a significant role in that, whether it's biology or computing, medicine or computing, arts or computing, and so on. And as my colleagues alluded to, is that we're expecting that discovery and innovation is going to be interdisciplinary, it's going to be multinational, it's going to be multi-institutional and multicultural. With that context, I wanted to spend the next few minutes just talking about some of the trends and advances that are shaping computing and communications in the coming decade and how it relates, in fact, to cyber infrastructure and interaction with other sciences. And just let me give you a few examples, and I'll dig deeper for a couple of minutes into a couple of them. Think of, for example, the exponential growth that we've seen in volume and complexity of data, as Alan alluded to it. Universal connectivity and ubiquity of broadband access. The melding of physical and cyber world that we have seen that's really changing many aspects of our approach to daily life, not to mention the research that we do. Explosive growth of sensors, mobile devices, and distributed low-power sensors and devices I mentioned. Emergence of cloud computing, which I know is of direct interest to my colleagues at Michigan, or is the transformation of communication, media, entertainment, public discourse, and the list goes on and on. And in a number of cases, what we've seen is that many of the technologies and solutions that the folks in the computing discipline have been talking about, from machine learning to robotics to speech recognition to augmented human capabilities, are all gone mainstream. It's become broadly applicable. And we're also seeing a transformation of commerce and acceleration of globalization as a result of some of these advances. I want to spend just a couple of minutes highlighting a couple of these areas that I described. One of them has to do with the explosive growth in size and complexity and the data rates that we're seeing. We're in a period that others have observed as being called as the era of observation or era of data and information, if you will. And actually, the truth is that we're drowning in data tsunami, if you will. And this is happening as a result of infusion of computation into science and engineering and the way that it's revolutionizing scientific discovery and innovation. And there's also a direct shift into automatic extraction of new knowledge about physical world, about the virtual world, biological world, and so on. And a lot of this is enabled by data mining techniques, new machine learning techniques, discovery and visualization techniques, together with emergence of multi-core architectures, virtualizations, and some of the advances that we have seen in server architecture. And something that relates to that, having to do with explosion of data that we're observing, has to do with availability of all sorts of sensors. As someone once said that revolution in science are often preceded by revolutions in measurement. And we're seeing that, in a sense, by access to various kinds of data that we have, whether it's video, audio, weblogs, twit, geospatial maps, experimental platforms, simulation and modeling tools. All of these are contributing to sort of this data tsunami that we're dealing with. And then Alan mentioned there are lots of opportunities in terms of managing the data. How do we deal with disparate sources of information, machine learning techniques, data mining techniques, not to mention new collaborative tools for doing e-science, some of the ideas that Dan Atkins had been talking about for a number of years. The other area that I want to highlight very briefly has to do with the transition that we're seeing from workstation or PC age to the utility age. The idea of providing computing power, like electric power, is not new. It's been around for 40 years. In fact, we can debate whether cloud computing is a new idea, it's a revolutionary idea, or an evolutionary idea. I'm reminded of a quote by John McCarthy, who's a famous computer scientist in the 1960s, who said, computation may someday be organized as a public utility. And I think we're very, very close to that. In fact, major cloud service providers such as Amazon are now able to provide vast amount of computing resources to various kinds of organizations. Just to give you an anecdotal example of that, each day Amazon adds enough computing resources to power one whole Amazon.com circa 2000. Each day they're essentially adding that much computation power to the resources that they're making available. And of course, what's really unique about this is that there's a compelling new business model which relates to the mindset shift that we've seen from asset ownership to utility-based and economies of scale that you get through access to power, cloud computing. Lots of interesting research opportunities, of course, beyond the fact that we're going to need to see advances in virtualization, advances in architecture, but also we're going to need to see potentially to be able to scale to the kind of systems we're talking about. We're going to have new programming models, new abstractions for developing essentially new software, placement strategies. If the cloud services are going to be as reliable as our electric power, that means we're talking about systems that are going to have the uptime of 5 nines, if you will. And of course, there are all sorts of workload issues, there are all sorts of privacy and security issues that have to be addressed. Just to wrap up, I want to highlight the fact that this is a golden time for innovation in computing architectures and software. As we see the end of exponential growth in single processor performance, especially as Moore's law is expected to come to end, we're going to have to see the next generation of discoveries that will require fundamental breakthroughs in both hardware and software architectures. And that will include advances in algorithms, parallel architectures, computational models, and programming languages. And these are some of the things that, of course, the computing community is working on, and these are reflect some of the activities in our portfolio. With that, I stop.
Thank you very much, Farnham. Tim?
Sure.
My turn. Well, very interesting to listen to my colleagues too. So thanks for inviting me here, Dan. And I think we'd be remiss without acknowledging your leadership at NSF in terms of bringing together a vision for cyber infrastructure that, as you've already heard, is pretty exciting and moving quickly. I'd like to give you an example of how it's playing out in the geosciences, which is my directorate, where, of course, we have a strategic vision that is all about understanding the changing and complex planet on which we live, which is changing actually furiously quickly. Just to give you a number, 0.1 degree global mean temperature rise per graduate student cycle is a good reference to think about. And so we need to understand in detail what is happening with our water, with our soils, with our rivers, with our air quality, etc. And this is a very urgent need to inform society in critically important quantitative ways. And so just to give you a sense of where the geosciences is and why we are, I think, both a driver and a consumer of cyber infrastructure, we're spending in geo about $100 million a year on cyber infrastructure. That includes, of course, supercomputing at NCAR. We did a recent back-of-the-envelope calculation that showed that about 30 petabytes of data regarding the Earth system are being transferred, not stored, transferred from institution to institution. And that rate is going up at about an exponential rate of about another 30 petabytes per year. So we're assembling a massive quantities of information about the Earth as a system, and this, of course, has international ramifications. We just did an agreement with the European Commission on coordinating our environmental cyber infrastructure in a systematic way. It has implications for interagency collaborations. We're to provide decision support and assessments. And of course, there's a lot of real-time, just-in-time needs as well. For example, when the oil spill happened, we had 5 ships down there at different times. We're measuring radionuclides in the water off the coast of Japan. And we have to be ready to deal with hazards, including things like tsunamis and earthquakes and hurricanes, etc. So we're taking this on. We have what we think of as an era of observation as well. We're deploying many sensors around the Earth. For example, in the ocean, we're going to have over 800 real-time sensors, 24/7, that will be commandable. There'll be commandable, deployable assets, robotic vessels in the ocean that will be commandable. We're looking at similar things for looking at the function of the world's ecosystems. And so there's going to be an explosion of information and data. And of course, simulation is driving a lot of this too. And to give you some numbers, the new NCAR machine, which will open up in an EPSCoR state in a few months, is going to be a 1.6 petaflop machine, LEED certified at the gold level, so it'll be a very green supercomputer center. It will have 130 petabytes of back-end data repository. It'll have 170 terabytes of memory, and it'll have a real-time disk of about 13 petabytes. So these are very big numbers, and it combines a much more balancing between the data access, the data utilization, and the computation, which is going to be really needed in the future. So we have a lot of challenges ahead of us, and we are deeply engaged in this. And I just wanted to highlight a new partnership where Alan Botecki and I are working in a new partnership between Geosciences and Office of Cyber Infrastructure, because we feel that we are ready to take this to the next level. We, like many other scientific domains, are made up of subdomains. We have the hydrologists and the seismologists and the atmospheric chemists and so forth. And those individual disciplines have developed their own solutions for cyber infrastructure and providing data resources and simulation. Now we want to look at the next meta level of organization, since we're all about looking at the Earth as a system and how humans interact with that system. So we've challenged the community through a new process, which really uses a lot of social media. It's very different from the typical NSF developer solicitation, do a review, select winners, and then over 3 years develop a new thrust area. This is what we're calling the Earth Cube, which is going to be a persisting, long-term, decadal cyber infrastructure for all of the geosciences. And what we're looking at is a community-designed, community-developed, community-governed, persisting resource. Other agencies are joining in with this, and other countries too. And we're doing it online with a social media approach. We have over 500 community members developing requirements, commenting back and forth on what those requirements mean. On a website, we had a recent workshop where hundreds of community participants came up and shared their sense of what requirements are going to be needed. And we're going to be funding several eager proposals in the next month or two to develop the first prototype design work to bring together a common cyber infrastructure for all of the geosciences or for all of the Earth system sciences. This is very exciting because we've generated numerous white papers, maybe 20, 30, 40 white papers, very detailed requirements. The community is responding to those requirements. We have a moderated social media website that's very active and engaged. And so it's a different approach. We're going to have another event in May where we're going to launch really the prototyping activities for what we call EarthCube. And so we see this as actually, the hypothesis here is that we're ready to do this, to get to this next level. The anticipated outcomes would be to really transform the conduct of research in the geosciences by supporting the development of a community-guided, persisting, a comprehensive cyber infrastructure to integrate data, simulation, information across the geosciences. Because if you think about it, as we make societal decisions in the context of a planet with finite resources and a lot of changing perspectives, we're going to need to have the ability to integrate, to do all the things that my colleagues have spoken about in terms of data mining, visualization, projection, access, in a very seamless way. But it's got to be a public good. It can't be a proprietary system that is exclusively held by a fragment of the community. And so we're launching this as an experiment, but I think it really does speak to the original vision that Dan brought to NSF of world-class, persisting, comprehensive cyber infrastructure to transform the conduct of scientific research. And I'll just stop there.
Well, thank you, Tim. And I didn't pay you to say what you said. And finally, Ed Seidel.
Hi, Dan, and hi, everybody. Thanks for giving me a few minutes as well. I'd also like to say thanks to Dan for getting the Office of Cyber Infrastructure really started and off to a very good start. And we all, I think, here at NSF see it as a kind of a rallying point for support for the future of science and engineering. And the assistant directors and the directorates and the divisions are working very well with the office in order to develop the continuing vision of what that will be. I'd like to tell you very specifically about the activities that I now oversee within math and physical sciences. We have within the directorate 5 divisions, which in some sense we think of as a basis set for doing all other kinds of science. We have mathematics, physics, chemistry, materials, and astronomy, and they have rather different cultures. And at the current time, or at least the traditional approach for these different disciplines, they're all compute and data intensive. But increasingly, we're looking at ways for them to work together to solve more complex problems. But right now, we have several different classes of activities. One is we have science groups that work with very large instruments, or, for example, large telescopes that produce huge amounts of data, or things like the Large Hadron Collider, again, producing a huge amount of data that then is distributed around the planet. And in fact, the warm-up run for the Large Hadron Collider last year for one of the experiments, one of the major experiments, generated 7 petabytes of data that were then replicated numerous times around the world, producing 35 petabytes of data just to sort of test out the machine. That data were distributed around many countries, and in fact, something like 10,000 scientists. And so it's quite an amazing just technological feat as well as a sociological one. So that's one class of activities that are primarily found in physics and astronomy, or doing very large simulations of things on, say, large supercomputers. So that's one class. And completely different approach is what we find in chemistry and materials. Although they do have some of the things I just talked about, they also have many thousands of different groups working on sort of smaller scales, whether they're experiment or theory computation, but many of them generate a large amount of data that then collectively has to somehow ultimately be shared among the communities in order to really share knowledge and to grow the science capabilities. But it's from collecting lots and lots of smaller kinds of activities of data, and is very largely data intensive. And even in the areas of materials where you might think of them as being highly simulation oriented, and some groups are, what we're finding is that those groups are actually producing data from simulations of materials properties. And then the idea is, how do you actually share that data with other groups so that we can understand in a more systematic way what are the fundamental properties of materials. And then we have this third class, primarily in the mathematical sciences, where people are thinking very deeply about what new kinds of mathematics and statistics are needed almost as methods in order to attack the other areas of science. And so these are 3 different approaches that are all found within the Directorate of Mathematical and Physical Sciences. Now, increasingly, we're finding that people have problems that, of course, go beyond the boundaries of any one of these disciplines or any one of these approaches. And so we're looking at complex problems that often require a highly integrated approach. So, for example, in my own area of computational astrophysics, for many years, people were simply, in quotes, trying to solve Einstein's equations, which are very complicated, and they tended to take up very large supercomputers with a lot of memory and a lot of computational power just to solve that. After a couple of decades of doing that, that's basically been done But now we want to branch out and apply that knowledge into many areas of astrophysics. So, for example, a gamma ray burst problem requires people not only to be able to solve Einstein's equations, but then you have to couple in radiation transport. You have to understand about how neutrinos play a role. What are the nuclear equations of state? What about magnetohydrodynamics and so on? And so every one of those areas that I mentioned really comes from a rather very different community within astronomy, physics, applied mathematics, and so on. And in order to look at a problem like a gamma ray burst, you have to integrate all of those areas of science. And we do that not only through meetings and so on, but by developing cyber infrastructure that allows people to share, whether it's software and the knowledge that's incorporated and encapsulated in the software, or through instruments. So some of the instruments I mentioned before now have to be integrated in order to understand what's happening, and perhaps in real time. So we have instruments now scattered across the planet. At the South Pole, there's a neutrino observatory. In South America, there are a number of optical and radio telescopes that are each generating huge amounts of data, and so on around the world, gravitational wave observatories. And all of these are either online or coming online. I'll point out one instrument in particular, which is the thing called the Large Synoptic Survey Telescope, which is in a planning phase, but within this decade, if all goes well, that facility will be operating from the Chilean mountaintop, and it will be generating as much data every single night as the Sloan Digital Sky Survey did, which was the most advanced survey project in astronomy, as it did in a decade. So you have a decade's worth of data collection, 40 terabytes, being generated every single night by a single telescope. Completely changes the character of how people will do this kind of observational astronomy. They won't be lining up to share time at the telescope. They'll simply be trying to get access to the data. So we have to serve all of that up. And we have to integrate all of those activities, whether it's simulation of all those areas for a gamma ray burst or all the observations, in order to understand, for example, a single thing like a gamma ray burst. So this leads to an approach in cyber infrastructure that we have to think about, not just, as Alan said, integrating in software or computing or data, but also large facilities. And so it impacts the way we think about developing the cyber infrastructure and the sharing policies and so on that go along with these communities in order to share the kind of information that they need to do the kind of science they want to do. So we see this, I use the gamma ray burst problem as an exemplar, but we have the same thing in material science or in chemistry. So we see these problems everywhere. So this brings up the idea of grand challenge communities, the enabling of different communities to come together to solve very complex problems in science and engineering. So this means we have to think about this at the cyber infrastructure level. How do we provide the ability for these different communities to be integrated? So we want to think about the instruments, which tend to be now more silicon than steel. They're perhaps in some of these cases, these are billion-dollar instruments, of which hundreds of millions of dollars could be provided just for the computing and data analysis environments and the networking that are needed. We have to think about integrating those kind of facilities not only to a national cyber infrastructure, but all the way to the campus level. So many of you will be engaged in some of these projects, and you have to then think about how to actually get the data to my desktop from these remote instruments, or how do I combine that with the supercomputing facilities and so on. So the campuses have to be now seen as an integral part of the entire cyber infrastructure that we're deploying. And we're going to have to develop partnerships between the federal agencies and the campus level. So we're going to all have to do our part in a coordinated way. I think this ultimately leads to the idea that we need to have a kind of an architecture for cyber infrastructure where we understand how the different pieces are going to have to plug together. And we need to develop the kind of mechanisms, policies, and even the APIs, the programming interfaces, to make that possible. And then as well, we have to think about how we support a new generation of scientists that are living in this environment. It's not like the old days where you thought the most important thing was solving your equations or looking at your particular problem. Your particular problem these days often involves integration of all of these assets, whether it's supercomputers or data archives or large-scale instruments, or simply working together with different parts of the communities. And they're often communities that you will never be able to actually meet with on a personal basis because they're too large. So we have to think about social networking and policies that allow people to share modules of software and data that are being generated and so on. So ultimately, we're thinking about a national system for cyber infrastructure that integrates all of these pieces, from software institutes to supercomputers to individual MREFC instruments, these large-scale billion-dollar instruments, and things all the way down to the campus level. And I think that's our biggest challenge now, figuring out how all of those pieces fit together and how to coordinate that. And I'll stop there. Thanks.
Wow. Well, thank you very much. It's really emotional for me to hear this coordinated, excited view, which is evolving at NSF. I wanted to point out for my colleagues at NSF that we have three plenary talks that in many ways illustrate aspects of what you're talking about. We this morning heard an incredible talk from Gerhard Klimek on the NanoHub, including extensive quantitative evaluation of the impact that it's having in the world, as well as extensive discussion of the social incentive structures of building a successful distributed collaboratory. Tomorrow we will hear from John Delaney on the Ocean Observatory and related activities, so stressing the importance of new forms of observatories. And then we will also, in the afternoon, be hearing from Victoria Stoden about the potential threat to reproducibility of science in the digital age unless we step up to many things, including preservation of code and data. So it's turning out to be an exciting and actually amazingly reinforcing experience. So we fortunately have, I also wanted to mention that the panel that we have from NSF are people that I knew and could call upon, knowing how incredibly busy ADs are. If we had had more time, we could have equally involved the head of engineering and bio, because indeed cyber infrastructure enables science and engineering and learning is pervasive across the entire NSF. So we have now a unique opportunity to ask questions to this distinguished group. So if you'd like to ask a question or make a comment, please queue up on either side and stand here and ask your question. Surely we do. Would you come forward? If you'd say who you are and your affiliation.
Yeah, I'm Gil Oman. Regards to some of you who know me well. This was a wonderful, wonderful opportunity for us to be in connection with NSF. I'm interested in the bio and genomics aspect, which will be one of the breakout sessions coming up. And I'm curious to the extent to which these many activities of NSF are coordinated with NIH.
NIH. So on the social science side, we have quite a lot of coordination with NIH, especially with a number of the institutes dealing with not only with social science questions related to population and aging, but also with neuroscience and computational questions related there. So there's really quite a lot in those areas. Gil, you know enough about the government environment to know that it's less than perfect and less than complete, but there's at least a lot of discussion going on and a lot of opportunities to share ideas and to talk about shared cyber infrastructure. Farnham will say, I think, can say more about what's going on the broader interagency front. But I know, again, from the point of view of SBE, the whole question of how we manage, analyze, discover things in data is something that is very broadly interesting across many agencies, and we recognize the need to work together.
I'll just chime in for a moment. There's increased collaboration between NSF and NIH, and I'll highlight a couple of activities. One is the National Robotics Initiative, which was launched last year involving the National Science Foundation and several other agencies, and NIH is also a partner in that. And there are 4 or 5 actually institutes from NIH that participate in this activity with NSF, NASA, and a few other agencies. And this is an example of the kind of activities that I expect you'll see more of that, involving various directorates at NSF and various institutes at NIH. Another activity involves the Smart Health Program, and again, there's significant collaboration between several directorates at more of these interagency activities. There's lots going on with other agencies involving my colleagues, and I don't know if anyone else wants to elaborate.
I'll just chime in. I'll just chime in briefly. So we also have within MPS a number of things, 2 programs in particular I'm aware of with the mathematics division and NIH in areas where mathematics and health sciences overlap, and also in computational neurobiology.
Can I say one more thing? Gil, it's nice to see you.
Hi, my name's Laura Patterson. I'm the CIO at the University of Michigan. And my question is, first of all, thank you all for the time that you've given us. What do you think are the most important things that a university should be doing now, both investments in technology, organization, and people, to prepare for and participate in the kinds of things that you've been talking about?
Let me just say a couple of things. You identified one already, which I think is the identification of people. I mean, you've got to invest in people and provide to get the expertise and capabilities you need. So I guess that's the first thing I would second your comment. The other one is I think you want to start looking at, as I mentioned, pick some key challenges or activities that you want to get done that have some near-term deliverables. I mean, what's difficult in this environment is if you pick a goal that's too far out, you never get traction. So can you find a way to get something that people want to see happen fairly quickly and build it like the sort of thing that Tim mentioned, the Earth Cube? I mean, so that people can have some understanding a year from now that they begin to see some things happen. So I think that'd be the second thing I'd mention. The third one really gets back to the other comment I mentioned my remarks, and that is governance. How do people have a way to provide input to the process? Because this isn't something you just simply plop on and say, here's a tool to go at it. It has to fundamentally change the way you do things. And so that's to be integrated into your expertise, into your plans, and the way you think about things.
I'd just like to add a couple of things. One is at NSF, we're looking for leadership from the community. And a university like University of Michigan could really help us with challenging the agency on how to really do this. The other thing I would say is that the not invented here is a real obstacle to getting to the next level of integration of science. And we're seeing this in our own directorates, we're seeing this across directorates, we're seeing this in interagency space, we're seeing this internationally too. And so we're really thinking through what the internet did for exchange of information. Really that model, we really need now to apply to science and engineering as well, so that you can actually do things. You can take the drudgery out of graduate student work, where the graduate student has to download and replot and reanalyze, spending 80% of their time doing that, to a higher level of organization. And I think individual universities have to be humble enough to know that they can't do it alone, but we need to have these networks of institutions, and even spanning country boundaries, to generate the kinds of standards and capabilities that will allow us to get to the next level in a way that's, as I said earlier, it has to be a public good. And so the competitive aspects really, in some senses, slowing us down. So please step forward, U of M, and you beat Ohio State. You can really show NSF what we should be thinking of next.
I'd like to add something to that too.
Are you there?
Just quickly. In addition to what Alan said and Tim, particularly picking up on people, I think it's often hard for universities to think about cyber infrastructure beyond the things, because you can sort of just purchase them. But the people that are needed to support these activities are really important. So that's one component I just want to emphasize. Another one is thinking through how you're going to be educating people. So what is the curriculum and what are the research activities in terms of training of students that are really important for the kinds of activities that we see coming. And we're talking about them being very integrative, very highly computational and data intensive. And I think it needs a really deep rethinking of the curriculum, the way students are trained, and also the way tenure and promotion policies are actually put in place, because quite often things are collaborative and it's not easy necessarily to get the credit according to the old measures of achievement that we often are used to. So we need to rethink that. And the last thing is just a practical tip. We had a task force on campus bridging from the NSF. There's a very deeply thoughtful and very lengthy set of recommendations on what campuses need to do in order to align their own local environments with the national cyber infrastructure, and what the agencies like NSF need to do to reach down. So I would urge people to take a look at that report and see how it might give you some guidance at the university.
So, hi, this is Gerhard Klimek. I guess you asked for a challenge. I have one for you. Since you are in the business of cat herding, the best way to herd cats is to move the food. So if you want to have science impact, you have to put an incentive system in place that converts the knowledge we have gained and are gaining today into other people's hands. And when I talk to NSF managers and say the biggest success of NanoHub is that we spend our money on the conversion of research results into things that are useful to others, I get kind of a bored look. And I see yeah, but where's the new science? What are the new tools that you create? I'm like, no. We worked our butt off in the last 15, 20 years and create things, and they go into our drawers, into a dead PhD thesis of software that nobody else can use, data sets nobody has access to, and we have no incentive system for these to be integrated into a day-to-day workflow. And as Ed just said, there is very little recognition in tenure cases that data or tools are actually, I think in many ways, better than the standard journal publications. So I urge you to move the food plates. Okay, that is, you can challenge us on the academic side as much as we want. We will go where you place the food. So rather than having the outreach program sort of the supplemental part at the end of a proposal, hold people's feet to the fire. What did they promise 5 years ago? What did they do with it? And seriously consider their outreach. Seriously put value in that. And then the tenure systems will also value it if you value it with where you put the money. I mean, you can't just say, you guys figure it out. No, you are in very, very strong positions at NSF. And really foster the conversion of knowledge for useful things into other people's hands. That's a key element. That's what engineers do, and that's what scientists also should do, rather than flying from the next flower to the next, oh, we found something new, cool, let's go to the next one.
Well said. I think we're all nodding our heads. I think NSF is really trying to be less risk averse, more incisive, more adventurous, and I think you've heard some of the things that are going on around the table. We're also talking a lot about data citation being a first step towards really providing that incentivization for getting involved, even at an early career level in this data-enabled science and engineering.
You will see coming up some changes very likely in the grant proposal guide that will help incentivize data, software citations, those kinds of things. So we're working on this sort of thing, the sort of culture change that's needed.
So let me add one other point. One of the things that you're going to see coming more and more from the project out of NSF is more emphasis on project management activities, because a lot of the cyber infrastructure activities are multi-year, in which we have to begin to look at exactly the sort of thing you're saying. What was done? Was it done on time? So you're seeing a lot more emphasis, you're going to see more emphasis from NSF on saying on the whole management process and follow, because it's essential to make it, at the end of the day, to make sure there's something there.
Can I also add that? In some of the new activities from SAIS, in particular in collaboration with OCI and engineering, you see that we're emphasizing transition from lab to practice and encouraging that and also resourcing it. And in fact, you'll see that in the new cybersecurity solicitation that just came out jointly with OSGI and Division of Mathematics. And you see that, in fact, there's a specific focus on how do we transition some of the knowledge that we create and make that usable to a broader community of users. And that echoes what some of my colleagues have said. I just want to add one more thing to a comment that Laura Patterson made. Laura, as you know, I served on the IT Council with you and Dan Atkins for the Provost IT Council. I got to tell you that I think Michigan is being very, very progressive in its approach to cyber infrastructure. It's very forward-looking. And what I would ask Michigan to do is, echoing what Tim has said, share that knowledge with other academic institutions, provide leadership to the rest of the nation. I think Michigan is definitely on the right track.
Thank you, Farnham. This is Brian speaking. Hi. It's moving to
Hi,
see
Brian.
everybody, you know, from Michigan and all our other colleagues there. Thank you very much. Just as one of the groups, one of the individuals has been involved, along with you guys, in helping Dan take us where we are today, I just want to say that you guys have kept this whole crowd in rapt attention. And that I think at the end of the day, this is a big tipping point for us here at the University of Michigan in terms of bringing us together across the schools and colleges with respect to centralizing and disseminating our leadership with cyber infrastructure. And we just want to thank you all for doing this and for having the connection that you do with us. I think it's absolutely great. You know, coming from the biomedical world, I can say that NIH, which might be not invented here, you know, we are learning from you, and the example that you're setting forward, we're trying to bring to bear here within our health system and then back and forth with the NIH so that we can bring the NSF vision and the NIH vision more closely together, just as we're trying to do here at Michigan, bringing the health system and the campus together. And, you know, so I want to thank you for, you know, helping us with this tipping point, because I think it's really coming together here very, very well. You know, the irony is it might have been easier for Dan to set the national agenda and get that going. Sometimes transforming things at home is a little more difficult, but I think it's really happening. Thanks.
We have time for one or two more questions.
Hi, everybody. This is Victoria Stodden. I was just at NSF yesterday speaking with a number of you, and it's a real pleasure to see you again, and you probably didn't expect to see me so quickly. So I really wanted to just make a comment. So something I've been observing as I've been watching this dialogue at NSF unfold and the impact on different campuses, and also down to the scientist level, is more and more the agenda and the trajectories that are being discussed are involving greater interactions with current regulatory structures. So I'm thinking about impact with IP law. I'm thinking about advocacy efforts that come to Congress mainly from particular vested interests, and they may or may not be beneficial. And I'm not going to name any names, but one of the more beneficial, say, is rare diseases. But they come from groups that may not be centered around the scientists. And I believe that more and more, as, for example, as Ed outlined, as we share our codes, share our data, as we are in a more open and immersed community, in a more networked community as scientists, we're going to run headlong into these regulatory structures that we didn't design, and we're going to have to deal with them. And I know NSF has been thinking about some of these issues, and so my comment is really that I think this is going to become an issue that probably deserves some consideration on its own, just in the sense of even down to levels of best practices for scientists, or how do we actually design these tools such that we can be respectful of existing regulatory structures and also help influence the structures that we are subject to as scientists trying to do good science.
One of the pieces of that, and thanks for that comment, and it really came out strongly from the EarthCube online discussion, is quality assurance of the data sets and the outcomes of these analyses is going to be extremely important. And I think that's something that University of Michigan could really help us with. I know colleagues there who've thought a lot about this. You know, it doesn't take much to devalue or discredit a scientific enterprise. And I think that the quality assurance of all of these integrated activities has to be really kept in mind right up front. And that's what our LithCube colleagues have been telling us.
So one point I would add is to follow on to Victoria's point is in terms of the regulatory environment is to think very hard, because so many of the data that we're interested in now involve people as dealing effectively with the protection of human subjects and dealing effectively with confidentiality and privacy as we begin to build ever more complex integrated data sets to use to solve really important grand challenge problems.
We have one final question from Brian, and then I'm going to wrap up.
Hi guys, this is actually a question. Is there any guidance you can give us in terms of working with industry or the establishment of public-private partnerships to achieve some of our objectives? It's an area that we're being asked to do, to participate in more, and I'm just wondering if you guys have any guidance on that for us.
Let me start with one, Brian, and one of the things that we're doing now is we're starting conversations with multiple cloud providers, because there is so much activity going on in the cloud and development of clouds and data centers that we need to figure out how to leverage that for science and engineering and education, and we haven't done that well yet. So we are starting a number of explorations to do that. Now I know SCI has done some of that in the past, so that's clearly a valid area because they're spending tons of money doing things at scales that we aren't even thinking about in some ways. We need to find a way to leverage it. So.
Yeah, in our case, we're beginning to do it, and I know engineering has done it for a long time with groups in industry who have interesting data about behavior. And we haven't used much of that in the past, but we are increasingly sensitive to the critical importance of data about the interaction between people and technology that private partners might have that is not naturally available in the scientific environment. So we're learning from this too.
Okay, well, thank you very much. I am enormously appreciative of your time today, and I agree with Brian. This has been a very impactful session. I also want to point out, I'll say the truth, I do own 100 shares of Google stock, but what we've used today is this Hangout video capability, and although it's only been two-way, and I took the safe route of having everyone in one room at NSF, although originally Myron was going to be somewhere else, I want to point out that this will work with up to 10 different people. It works very smoothly and robustly, and I'm starting to routinely use it. And so we could have had each of these speakers on their own machine, and as the voice actuation puts whoever's speaking up into the main thing. And so yeah, and I also want to show you the coolest thing about this, which is this mustache feature.
I was wondering what the mustache feature was.
And it puts a different mustache on. You can only put it on yourself. You can't put it on someone else. So if the meeting gets dull, you just start pushing the mustache button. Okay. Thank you very much, everyone. Thanks so much, colleagues. I really appreciate it. Okay.
So just a word to those of you who are staying for the afternoon sessions. We are now going to be having concurrent sessions, so the walls will be inserted here, and there will be 3 sessions in these different rooms, and then 1 in Forum Hall. So if you brought your printed schedule, have a look at see what room you're in, or there is a sign at the near registration with room locations.
Well, let's take this chance to give a big round of applause for Catherine Lawrence, who's been who's the production manager for CIA Day.
Thanks. And then after the first round, there's a networking break, so there will be snacks over in that area, and you'll have about half an hour to mix and mingle and get to know your friends. And did you have another announcement too? Oh, and there's tons of extra food. So if you're leaving, take a bag lunch to your grad students, your friends, your children, your husbands and wives and boyfriends and girlfriends and whatever. Yeah, so we start at 1:30 in the 4 rooms on this floor.
Okay, so welcome to our first concurrent section, Genomics, Research, and Computational Challenges. This is a 90-minute session. Our speakers for this section will be Guillaume Gavcole, Gonzalo Alcacis, and Andres Vizbicki. And I'll turn it over.
Thank you very much, and thanks to the organizers for putting this all together. It's been a wonderful day so far, and hopefully this session will be equally enjoyable. So one of the things that we kind of tossed a coin at the beginning to see who would go first, but in a sense, my talk is a very high-level overview that sort of sits at the bridge of a lot of the computational things that we've heard earlier this morning, as well as the genomics and biomedical side of things. And so I'm going to touch on a variety of things today and hopefully give you some food for thought towards the end. And I'm not going to go into a lot of experimental details or data today because this really is meant as a high-level overview of where does computation and genomics and medicine kind of intersect. As a bit of background, I'm the director of the Bioinformatics Core and a research faculty here in CCMB, our Center for Computational Medicine and Bioinformatics, and soon to be department. So overall today in this 25 minutes or so that I'm going to talk, I'm going to cover genomics and the technologies that are used for analysis and a fairly small subset of genomics. And I want to talk a little bit about setting the perspective of the past, present, future, because in essence, the things have changed a lot in the last few years, and I don't think we're done changing. So, and then I want to talk about the role of computation and analysis. So I'll talk to you about both about the analysis pipeline in a sense and how computation intersects that at different points. And then I really want to spend a fair bit of time talking about the challenges that we're facing because putting the challenges out there for people to think about and ponder about how do we address these challenges is one of the great benefits of having these CI days, is putting that information out there and letting multiple minds and good minds think about solutions. So, first of all, to set the stage in a basic sense, genomics refers to the measurements of either RNA, expressed RNA in cells, in tissues, genomic variations at the level of genomes, looking within the genes themselves, or in many ways in environmental and other microbiological samples, whole genome sequencing, either de novo or with reference genomes. And so I'm going to use genomics in that loose sense. Many people would fine-tune that a little bit, but for today, give me the benefit of the doubt, and we'll look at this as a large picture. There have been a lot of trends over the last 10 years or so that have radically changed the amount and the cost of DNA sequencing. And it's hard to pin down the exact point, but I'm going to give an approximate 10-year time frame for this. And so I want to set the stage, given the nature of the season and the fact that we were dealing with past, present, and future, I want to bring you to a picture and a trend I'll have along here. First off, though, because I didn't know the exact nature of the audience today, I'm going to talk a little bit about terminology. As computer scientists and engineers, we oftentimes talk of mega, giga, gigawatts, gigahertz, gigabits, but we actually can get confused because we all get into our own jargon. And so I prepared this slide when I gave a lecture in a class a year or so ago, but it makes sense just to have in there. I won't dive into too much detail on it. But when somebody says, if they're in the DNA sequencing core and they said, yeah, I just generated, 100 gigs, they don't mean 100 gigabytes or 100 gigabits or anything like that. They mean 100 gigabases. And so we tend to put these prefixes in front of things and develop our own jargon. And so be aware that people can toss out the same terms and mean different things. Many people refer to, and this gets down into the biochemistry level of things, people will call something a nucleotide or call it a base or call it a base pair, and in general they'll mean the same thing. But as I was teaching to students in graduate school, I wanted to emphasize the fact that there are differences between them. We shouldn't lose sight of these differences and let the jargon degenerate. So make sure you're clear about what you're saying when you say it. And I won't go into any further detail on that unless somebody wants the biochemistry lecture, and then we can do that at the end. So in the ghost of Christmas past, we think, and it's not that far ago. This doesn't reach 100 years into the past. Sanger sequencing was first published in, I believe, 1977. So that isn't that long ago. And as recent as the Human Genome Project, most of the sequencing was done in fluorescent capillary well sequencers that could do 384 clones one in each well per run, and they could run many of these runs in a day, and yield about 700 to 900 base pairs of bases of DNA. and they were read by fluorescent image. And so the total output from perhaps a week of sequencing might have been 2 or 3 gigabases of DNA. And the output of that would have looked like these fluorescent grams, and you would call the bases depending on what color it was and where a peak was detected. So the present, and in some ways the ghost of present, is that we're in a position in technology where we have massive parallel sequencing of shorter fragments. So we're not going to see these large 700 and 900 base pair pieces, but we've made several advantages and changes in the technology. Number one, the fact that you don't need to subclone the DNA to start with. Now, for those of you that haven't been in the lab and used pipetters, what we mean by this is that in the past we had to take DNA, break it into pieces, and clone them into a bacterial vector, grow them up in bacteria in little cultural tubes, isolate the DNA, and then sequence it. So the number of steps and the amount of time it took and the amount of robotics and reagents was quite high. Now we can take this DNA directly, add linkers to the end, amplify it, and sequence it. The cost per megabase of sequence has gone down dramatically. I'll show you a graph that is almost hard to believe, but it is true. And the amount of megabases of DNA per day that can be generated with this technology has increased as well. I will say as a caveat, there's been a slight increase in the error rate per base, but the amount of data that is generated is so high that those that don't match can be filtered out and discarded without a high loss of, or without a large loss. There are many of these platforms available. I'm not going to I'll show you some of them today, but I'm not going to discuss any of the specific technology platforms. Just to give you a sense of how much data we're generating, in the past I said that a Sanger sequencing run might generate 2 gigabases or 3 gigabases of data in a week. A HiSeq run, as I'm going to show you here, this HiSeq run, HiSeq 2000, 1 lane, and there are 8 lanes of it, so multiply this by 8, generates about 1.5 1.5 times 10 to the 8th reads per lane, multiplying that times 8. So the amount of data we're generating is almost on the order of 100 times larger than what we were getting out just 5 or 6 years ago. If each of these is only 100 nucleotides long, we can actually generate 3 times 10 to the 10th nucleotides in a single lane of data, multiplying that by 8. So we're upwards of almost hundreds of gigabases of data that are generated. A run takes about a week, so you have to factor that time in, but still the amount of data being generated is significantly higher than the past. Given this and the coverage calculation on this slide, the size of the human genome is large at 3 times 10 to the 9th nucleotides, but as you can see with some of the numbers we're generating, we're actually getting upwards of almost a genome size of nucleotides per run. And if we're only looking at the RNA or the exomes, we can easily look at somewhere around 500x coverage per lane of sequence. So the numbers vary widely from the labs, but that's the general order of magnitude is the amount of sequence being generated. While we cannot sequence a single individual in one flow cell yet, we're probably getting closer, and I'm sure Gonzalo will talk a little bit more about some of the throughput from the 1,000 Genomes project. Here's the slide that's a little hard to believe, and as we heard this morning, and we saw the actual notes from Gordon Moore's lab notebook, this is a line which draws in some ways Moore's law, which is, it basically deals with the decreasing cost of production per transistor. In this case, it's the cost of sequencing per megabase of DNA sequence, and this comes from the Human Genome Research Center, and in this case, you can see that if we look back only as far as 2001, this does not go back to prehistoric times, but we were dealing with just under $10,000 per million base pairs being sequenced. And then somewhere in 2007, as next generation sequencing really hit the heyday, the amount of the cost per megabase, you can see precipitously drop. The slope changes dramatically here. I'm not sure it's quite down to 0 yet. I believe this is a slight artifact of the graph, but the slope has stayed the same, and so we're down probably almost a 1,000-fold decrease in the cost per base in just the last 4 or 5 years. So I don't know that slope was going to get any deeper. Otherwise, it's going to go the other direction. And yeah, and I'll talk a little bit about my ghost of the Christmas future. Thank you for that segue. So this is the ghost of the Christmas yet to come. And in the future, one of the things that's out there right now, and it actually is here, is single molecule sequencing. And currently, that we have a Pacific Biosciences or PacBio machine here on campus, and we're beginning to pilot data coming off of that. There are some sequences available. Right now, the current error rate associated with the long reads makes it not useful for really, really long reads. You have to actually circularize the reads and do a lot more. I won't go into that technology. But there needs to be some improvements in these single molecule sequencers. In the past, what has happened was, and to get into the technology a little bit, in the massively parallel sequences, you put millions of isolated clonal forests of the same DNA molecule on a glass slide, and then the polymerase is in the solution around that. In these single molecule sequencers, and I don't have a diagram of it in my slides, the polymerase itself is actually is anchored to the surface of the flow cell, if you will, or the surface, and the DNA passes through that. And so we're beginning to see changes in the technology. Some of the future ones include, there's a company called, a technology called nanopore. In this case, the DNA is actually passed through a pore in a membrane, and the changes in ion potential are measured. Visagen is another one that is dealing with a slightly different technology, and there are some coming out that deal with sequencing by massive hybridization to probes, mass spectrometry, even electron microscopy or atomic force microscopy. These are ones that aren't even named as technologies yet, but people are investing in them. And fairly recently, the Archon X Prize was announced, and the contest will award you $10 million if you can come up with the following. You have to sequence 100 human genomes within 10 days or less, with an accuracy of less than 1 error in 100,000 bases, covering 98% of the genome, and at the cost of less than $10,000 per genome. Which I think all of those together, there's a lot of tens and hundreds in there, but that's a pretty high challenge given today's current technology. What are you thinking, Gonzalo? Think you can do it? Okay. All right. Here's a slide that I have to change every 6 months. And that is actually one of the problems being in this business, is that I can't use the same slide deck from year to year. People catch me on it all the time. Now, that technology's gone. This one has changed. Where's the new one? And so every time you give lectures and talk, you have to actually change your slides. And so I've had to take out technologies and add ones in. In fact, I believe I don't think there's a Helicos machine out there right now. I don't know quite where that company is at anymore. Pacific Biosciences. Life Technologies, Ion Torrent, as well as the Applied Biosystems. So there's a lot of different platforms. Each of them have their pluses and minuses. My talk is much too short to go into all of that, but it is out there to know what the different technologies are for the choice. But all of them are generating a larger amount of sequence and have different pluses and minuses. But all that technology has to be applied to biology in some way. So genome resequencing is probably the largest amount of stuff that comes into our bioinformatics core. RNA expression, ChIP-seq, protein binding to DNA. These are things that are out there, and then the technology is being applied with high throughput sequencing. So what is the role for computation in genomics? And I think my number one right now, my day-to-day challenge is storage. And that is the fact, how are we keeping this data and where are we keeping this data? A single run, like I was referring to, that one lane that generates gigabases of data, a single run from Illumina with all 8 lanes generates almost 1 terabyte of data a week. And you have to hang on to that data and do something with it. When you actually process the data, you increase the size of the output files. And so a lot of times now, so storage is a challenge. I'm not sure that's an insurmountable one. It's just, it remains a challenge. Data transfer. I refer to SneakerNet and FedExNet. Because while computers are great and networks are great, if you're transferring 2 or 3 terabytes of data, it's still faster for you to put it on a removable drive and walk it over to my office. Or if you're going to put it across the country and you've got 10 or 100 terabytes of data to transfer, it makes more sense to actually move the drives than it does to ship the bits across FTP or across internets at this point. Those are 2 challenges in the initial data, but once we actually get the data in hand, aligning data to reference genomes, assembling the reads, whether you do it to a reference genome or de novo assembly, calling peaks, calling the transcripts, and right now visualization and the downstream analysis once you get the peaks called, determining the sequence variants, copy number variations, structural variations, all of that remains to be computationally. As of now, in the software that currently exists out there, the aligning reads to reference genome is a parallelizable a process. Assembly of reads de novo may possibly be parallel ready, but it's not quite now. Most of it requires these large de Bruijn graphs and graphical structures requiring lots of memory. So there's still a role for computation, but there isn't one clear pipeline, one clear cluster analysis. I'm going to skip through this. I will talk about this as we go, and I'm running a little short on time. The data itself, when you get the data out, actually looks like this complicated slide. This is a FASTQ format where the nucleotides that have been read by the sequencer are here along with quality scores. I won't go into how the quality scores are presented here, but they're the probability that the base is called correctly. And it's in what's called the Phred notation from the old human genome days of Phil Green's editor. And they're in the same vein of the probability of error model. So because we have quality associated with these, we run some QC on these reads as we get them. And given the length of the sequence read from left to right, and the box plot here represents the error that we see, the mean error and the related error associated with all of the reads in the entire run, so we get a sense of overall quality. The aligning and assembling of reads to a reference genome is really the next major step that we do computationally. If we've got a de novo organism or something where we don't have the genome, or we're looking for something very novel, we can do de novo assembly, not using a reference genome, but actually using the reads themselves to create the assembly. And there are numerous different tools available for this mapping and aligning. We primarily use either Bowtie or BWA for our aligner, for reference-based aligning, and for de novo assembly, Velvet, Abyss, etc. Really? Okay. Okay, I got 9 minutes left and you got 1, so we're going to average. I'll go just a little bit over and go quickly. Sorry. I'll skip how we reference them. There is standard formats for reporting the alignments of reads, the SAM, sequence alignment and mapping format. The links are in my slides. There are a lot of tools that we use for the downstream analysis. After we align the reads to the genome, that is relatively easy these days. It's computationally somewhat intensive, but it's very doable. But each experiment that comes in requires a different analysis, and there are a lot of different tools for the downstream analysis of genomes. And visualizing the reads, while a lot of the analysis is still done in tabular form and a command line, a lot of times you want to look at the reads and see and verify for yourself. And so there's a few tools that are available that are also listed in my slides as well. Okay, I want to get into the challenges though. So there are 3 major challenges I want to point out today. The first I've already alluded to, and that is the data issues, storage, the access to the data, transfer of data, life cycle, how long do we keep it, and eventually privacy and risk associated with data. How do we translate what we're doing at the research level into medicine and applied medicine? And the second is the accessibility and usability of this data and the computational tools. And that's really a main one for this audience. There's another graph that is somewhat scarier than even the first one I drew about the cost, and that's at the amount of data being generated. And this graph shows, this is taken out of Lincoln Stein's paper from about a year ago, but it basically shows that in the olden days of Sanger sequencing and pre-next-gen sequencing, the slope of the increase in the amount of data was actually below the slope of the cost reduction in the amount of storage. So it actually cost you less next year to store it because the price of storage disks went down. Somewhere around 2004, 2005, the inflection point changed with next-generation sequencing. And the rate at which we're generating data is now exceeding the cost reduction in storage. And so it will cost you more next year to store the same amount of data because, it'll cost you more next year because you'll have more data and the disk prices aren't going down fast enough. Okay, privacy. This one I really want to get to. I may skip through some of the others, but while DNA itself does not identify a person, if the pattern in DNA can be detected and compared with another pattern, you can actually say that this is the equivalent of a fingerprint. And so the point at which we can link 2 samples together and say they are identical can be considered an identifier. And there's an ongoing national discussion about whether the DNA sequence information will become one of the HIPAA identifiers, which will then cause us to have to deal with the data in a different fashion in order to comply with regulatory guidelines. And so that's just an awareness piece that's out there. It isn't law yet, and it's still under discussion, but it may change how we have to handle data and what we have to do with it. Translating results to medicine, linking genomic data to other health information. How do we integrate genomic data with other patient data, disease state, progress, efficacy of treatment, phenotypic measures, and that leads us directly to personalized genomics. How do we actually take this data and look at individual people and their family structures, their susceptibility or their susceptibility to disease or their possible treatment route? And then I think this is still on the horizon, but not that far on the horizon. It's kind of like snow. It sort of shows up right before you expect it to. But genomic data is part of the electronic health record. Will we actually carry around with us on our iPhone someplace an application that contains portions of or all of your DNA sequence as part of your health record? And how will we deal with that information and data? Finally, yes, there is one tomorrow on that as well. Finally, I think for the bringing communities together, biologists, and I won't insult the biologists in here, but biologists on average are behind the curve on learning, adopting, and using high-performance computing, especially clusters, schedulers, PBS scripting. If you talk about PBS scripts in front of a biologist, they say, wait, is that phosphate buffered saline? Or, you know, in other words, the acronyms collide again. But on the other front, I think we have to bring the groups together because not every problem can be thrown at a cluster. And so we have to bring together the communities and come up with ways. And I think that in a lot of ways, what we have to deal with are my two subpoints here, which is there is a learning curve and an onboarding process of getting biologists to use computers to better their advantage. And the second is we need to develop more diverse, flexible, and adaptable resources for storage, networking, and processing of data. And I think those are the two biggest challenges. And in one way to address those and where we're proceeding with this is that there have been some changes in the last year or so with a new MSIS structure and the new med school CIO, Ted Hans. There's been investments in both personnel and computing resources, including Jeremy's in the audience here, a high-performance computing specialist for the medical school, helping to bring people to Flux and help bringing Flux to us. There's a new Department of Computational Medicine and Bioinformatics, and there will be a new Bioinformatics Core, both of which will be kicking off in January. And so those are kind of shameless plugs, but at the same time, understanding that there is a commitment here at the university for doing this, and there are mechanisms for bringing more and more of researchers together with this computational infrastructure. And I think for the sake of time, I will stop there and take any questions we have. All right? Thanks. Thanks. Quick questions before we move on?
Jen, what do you see as your biggest challenge going forward in the next couple of years, other than cloning you?
I think it's going to be dealing with, we can align sequence reads to genomes. We can do a lot of that. There's a couple areas where I think we're going to see big need for change, one of which is in metagenomics and sequencing of community structures, because that remains kind of a black box of understanding. How do we understand what's going on with the whole community of organisms? And secondly, I think the diversity of downstream analysis, what we've done is move the bottleneck forward. We now can sequence the heck out of things and get lots of data. We still have to analyze it and then apply it to biology. And so I think there still remains a large black box of biology. And I think if I were standing on a soapbox, which this is kind of a large soapbox and I get a chance to do this, is to say that I'm cautiously optimistic that high throughput genomics can actually help us address the black box of biology in terms of what proteins interact with what proteins, what's in a pathway, what is disease causing, what are the relationships and interdependencies between disease and biology by actually tapping into some of the high throughput data. So I think that's a challenge as well as a possible bright light. Yeah.
What do you think about on your third point there, the platform, say Galaxy for data management and addressing that need? I guess what further is needed beyond something like Galaxy? I guess is kind of my question for what you're talking about. Or what further is needed?
Galaxy, I think, is a good starting point for a set of tools wrapped up. I think it covers a lot of the very basic things that would be done. I think one of the concerns I have is where is the data being stored and for how long and who has access to it. As we go forward, we're going to have to look at the data management side of things and the data lifecycle side. And Galaxy doesn't address that really well. You still have to upload files and move things back and forth, either in and out of a public server or your own server. And then the question is, how long can you leave it there? The compute cycle actually is less of a demand on things these days, although you still need a lot of it. I don't think we're running out of compute cycle. I think we're data movement, data storage is a bigger issue. But Galaxy represents a good starting point. I think right now the only problem I have with Galaxy is that it has a fairly defined set of tools, and when I want something outside of that, I have to then take everything out of Galaxy, go someplace else, and bring it back in. Or I have to spend the time to write and wrap what I want and put it in Galaxy, and I oftentimes don't have that time. But that's, I think a set of tools like that might be beneficial. GCG was used for a long time, and it became a very de facto set of tools, and Galaxy could easily become that. So, Lee?
Given that the SRA is basically being phased out and it's kind of on life support right now, what do you think the future is for data
So I wish I had the NSF guys and some NIH guys videoed in to ask that direct question. Long-term storage and public repository that extends beyond the grant life cycle is an issue in public funding right now. I don't know. I don't know what's going to happen with the Short Read Archive and the public repository for data. It's an enormous amount of data to try and hold, and unless you have some sort of policy towards it, I think we won't see it today, but at some point you're going to see some kind of compression strategy where we don't store all the genome, we store what's different. Or something like that, that something's going to come forward. Either that or somebody's going to invent the Star Trek Ridgeline crystals and we can store a lot more data in a cube. One of those things. Chris.
I've actually heard that UCSC is building Genome Hub and they will be transitioning SRA over into the Genome Hub. I don't know where that's at.
Okay.
But along those lines, one of the things that UCSC is doing is providing an analysis environment, basically a cloud environment. And that, from my perspective, as a secondary consumer of data, not someone who's generating the sequences, but trying to analyze them. One of my biggest problems is actually the movement of data. I spend enormous amounts of compute cycles just moving data
Yeah.
from one place to another to do a trivial analysis that produces a very small bolus of data. So do you see a trend towards not data transfer but analysis transfer, where you're moving the analysis to where the data lives, not worrying about that?
You know, Chris, this came up as, this actually goes back a couple of years. I asked a similar question. There was a high-performance computing thing at Harvard, and a lot of big brains get together about this, and I said, you know, what are we going to do about moving this data faster, and can't we widen the pipe to send the data over there? And the guy just was kind of like rapping me on the forehead going, just move the analysis to the data. And so this is where I think that we have to be smarter about how we do the analysis. And I'm not against cloud, or I don't even want to take a stand on it, quite honestly. But I think that we have to address what are the bottleneck issues. And data movement of terabytes of data isn't going to get substantially faster. I mean, you can bond a couple of different FTPs. There's Globus FTP. There's things we can do that will incrementally, linearly speed it up. But when you scale, it still takes a period of time to do that. And is that worth doing relative to moving the analysis closer? And I don't have a solution, but I think that is a challenge. We have to address that because for doing one experiment, it's okay to move it and do one. But if you've got to do these things in a pipeline and repetitiously, you have to move the analysis close to where the data sits. You know, in our bioinformatics core, we have a storage array that sits right snuggled up next to the analysis machine, and I move the data once. I don't even move it into project directories. I create soft links and symbolic links. The data moves once because that's a cost. And I don't duplicate the data because it's a cost. And you know, if we get into issues of if Amazon becomes capable of taking on HIPAA responsibility and people are willing to move their data there and take on that risk, that's one possibility. But I personally like to mitigate risk by keeping things relatively close to me. I think that's more definable, but these remain possibilities for solutions, okay? All right. Thank you very much. Salo is next. And just tap the screen. Yeah.
All right. So I was asked to talk a little bit about how we're using next-generation sequencing to study complex traits. I think it's a varied audience, so I tried to first just give a high-level view. You know, what are the analysis steps that happen to the data early on, give you a sense of the computational cost for the data sets we're dealing with, and then walk through a couple of examples of specific analysis. You know, just to say, you know, like you heard from Jim, the scale of these data sets is just staggering. You know, so the first human genome was sequenced ending in about 2001, 2003. Took, you know, 5 years or something like that to do. We think that over the next year, we're going to have sequence data on something like 20,000 genomes to analyze here. You know, so the scale for that from that 1 to 20,000 is pretty staggering. Okay, so as you heard, you know, we have very high throughput sequencing technologies now. There's a number of commercial platforms that allow you to do this. The thing that they typically have in common is that the reads are relatively short. You get millions of them, and the error rates compared to traditional sequencing are relatively high, maybe on the order of 0.5% to 1%. You know, if you're studying human variation, if I compare DNA from any two individuals in this room, I expect to see a difference about every 1,000 bases. So an error rate of 1% means that I have 10 times more errors than real signal to start. So I get this pile of reads, and the first thing I need to do is to somehow align them relative to each other. Each read on its own has very little information. So the first step in these analyses is basically read alignment. I take each read, I try and place it somewhere in the genome, find the best matching placement. It's a relatively straightforward problem with good solutions. You might imagine that if you took tens of millions or hundreds of millions of reads and did the scan across the genome, it would be a terrible solution. But once you build an index of words and say, you know, for each 15-letter word or something, I'm going to list all the positions where it occurs, you can take your read, look it up in the index, and place it relatively quickly. So there are some nuances to this, because it turns out that placing each read on its own often doesn't give you a very good solution. And so after you do the initial placement, you typically look at groups of reads that align over the same location and try and refine the alignment. So here's an example. If you look at these bases here that are highlighted, they're highlighted because they would mismatch the reference. And there's a decision to be made, which is maybe instead of putting a mismatch, I can insert a little gap and remove the mismatch. Now, if I look at one read at a time, I'm going to say, well, actually, mismatches are more common than gaps. And so that would be the right decision. Once I see a pile of reads and I have other evidence that there is a gap there, I can resolve this, which would have been hard or impossible to do otherwise because it's at the edge of the read, and say that's probably a gap. So once we place them, we usually scan over them and try and refine the alignment in various ways. There's another kind of refinement that's similar, but that doesn't rely on having deep enough coverage of a location. And this is, you know, when you place a read, you can say something about how confident you are of that placement. And that's got things to do with, well, how much better is the placement that I chose compared to the next best placement, or the next best placements if you have many choices. It turns out that you can actually have uncertainty at the per base level. So it might be that you are very confident that the read maps there, but you're less confident about what happens to individual bases in that read. So let's focus on this little G here at the end. It's been aligned to a C. That's one possibility. Another possibility is to place a gap, just like before. And I have to decide between these two. If I have just one read, I'm going to make a choice, but I'm not going to have very much confidence in it. And so one way to do it, and here in this cartoon, I don't know if you can tell, but the G is shrunk a bit, is to say, I'm uncertain about that particular detail of the alignment, so I'm going to reduce the quality for that base, and I'm going to discount it when I'm using it to discover DNA variation and so on. And this actually makes a huge amount of difference. When we started doing things like this in the 1,000 Genome Project, we removed about half of the errors that we were making in calling variants. Okay, so assuming you do this, you can place the reads, you can refine the alignment, you can calculate this per base alignment qualities by summing over all possible alignments for each read and so on. The last thing you want to do is to call variants. You want to identify positions that vary and make judgments about those. So, you know, in theory, you might say, hey, I'll have a pile of reads at a particular location. You know, here in the position marked with a star, some of the reads say there's an A, some of them say there's a C, and I want to make a judgment about the individual that I extracted the DNA sample from, and that was used as a template for those reads. And the judgment might be maybe that the individual is a heterozygous, that he has a chromosome that's A and one that's C. But to formally do this, I'm going to build a probability model. I'm going to take the reads, calculate their probability given each possible true genotype. Before I have any data, I say, hey, any set of reads is equally likely, or they're equally likely given any possible true genotype. And as I accumulate, I say, hey, the first one says a C. What's the probability of that if the truth was homozygous for A, or if the truth was homozygous for C? With an error rate of 1%, those probabilities might look like that. And I gradually pile in the reads and update those probabilities. At this stage, I've got probability of the read set given each of these 3 genotypes, and I'm almost ready to make a decision about what to say about this Bayes. And what I need to do is to combine it with some kind of prior information. So I'm going to say something like this. Before I had any data, I expect that most positions would match the reference, because the reference is just a chromosome from a particular individual, and I know that any 2 individuals differ very rarely. So I'd say, without knowing anything, that I expect 999 times out of 1,000, the individual will match the reference for both alleles. And only 1% of the time would there be a mismatch, but most of the mismatches would apply to a single chromosome. So if I combine my probabilities I just calculated with these priors, actually I'd say, hey, with very high confidence, 80% probability, this individual is not a heterozygote. He's actually homozygous for the reference. Because of this very strong prior for matching the reference, to discover variants, one needs quite a bit of redundancy. In fact, to be confident of finding most variant sites, you'd probably need to sequence a single genome about 30x redundancy. And so your 3 gigs of data become 100 gigs of raw sequence for calling one genome. There's different ways to actually interpret this. And so a different way to take the exact same raw data, but to come up with a different conclusion is to say, hey, why don't I look at what happens at this position in other individuals? If it turns out that the position varies, and particularly if the position varies in individuals who have a similar flanking stretch of chromosome, I might have a slightly different prior. I might say, I already know that this position varies in, say, in this case, 20% of chromosomes, so I change my priors, and based on changing my priors, I can now actually make a confident, different decision. So it's the same data interpreted in different ways. Okay. So when it comes to studying a genome, these are the set of choices that you now have. So you can do deep whole genome sequencing. If you just take the data generation cost, if you are savvy about bargaining with the different providers, right now this costs about $2,000 a genome. It's the most complete analysis, about 30x coverage for the entire genome or something like that. You could say, hey, instead of trying to do this over the entire genome, because $2,000 still adds up, if I want to do this over 20,000 individuals, it'll be $40 million. If anyone here in the room has those $40 million, I'd be happy to take them. But if not, I can try. Anyway, so you could say, hey, why don't we focus instead of on a subset of the genome that's particularly interesting? So you could do exome sequencing as an alternative for quite a bit lower cost. Or you can say, well, I'm actually going to do the entire genome, but I'm going to do it at lower coverage, and I'm only going to be able to interpret it by looking for these shared stretches and so on. It turns out that now that there's enough sequenced individuals out there, you can actually build new kinds of genotyping arrays that look not just at common variants, but also at rare ones. And those are also kind of an interesting take on this. Okay, so just looking at what we've described so far, I'm going to try and give you a sense of what we use for our computing needs day to day. So we've got a compute cluster that's shared between my group and another research group in our department. We have about 2.5 petabytes of storage, 5 terabytes of RAM, and about 1,500 CPU cores. It's been customized quite heavily to support applications that do a huge amount of I/O. And we use Flux for overflow. So I think right now the maximum you can request from Flux is 500 nodes, and many months we request that. Most other months we request about 250. We're going to increase that. Good. We'll use it. So if you say, what does a project, say, with 1,000 samples currently take for analysis? So when we take, say, the current set of 1,000 samples sequenced by the 1,000 Genome Project, that corresponds to about 60 terabases of raw sequence data. If we transfer it in here from NCBI, for example, it takes about 2 weeks for data transfer with about 4 terabytes a day or something, so we can get. If you say, well, the initial placement of the reads, finding their best alignment, refining the alignment, and so on, takes about 300 CPU months over these 1,000 samples. Calling small variants takes another 200 CPU months, and calling larger ones takes about 300 CPU months. So I'm measuring this not in hours or minutes, but in months. It kind of works well. And then the final step where you kind of try and refine genotypes at each individual by looking for shared haplotypes and so on takes 400 CPU months. So if you had about 1,000 dedicated compute cores, you need about 6 full weeks of computing time to do this. And so that's one project, 1,000 samples. If you say, hey, what about if I want to do 20,000 samples over many different projects, it gets to be a bottleneck, and you see that, hey, it'd be good to think about ways to do this even more efficiently. And of course, you can get a lot of computing power going back to the Amazon cloud or something like that, but the costs are actually also rather high. So I think we estimate it costs us about between $50,000 and $100,000 for this 6 weeks of compute power on the cloud. Okay, so here's one of the projects we're involved in, the 1,000 Genomes Project. Basically, the goal here is to build a catalog of all genetic variants, and this is kind of an essential resource for disease studies. We published our initial report at the end of last year in Nature. We, at the time, had sequenced 2 small families. We call them trios in the genetics lingo, basically parents and offspring, and another 180 genomes. We discovered something like 16 million genetic variants. Some of these were single base, 15 million of them. Some of them were multi-base indels. If you go look right now, even though this paper was published in November, it's the highest cited paper in Nature for last year by a couple hundred or something like that. How much do we gain by doing these analyses? So if you looked at the data with a standard analysis that basically looks at a site at a time, tries to adjudicate what the genotype is, this panel here gives you the error rates. So the error rates depend on frequency a little bit. You can see that at heterozygous sites, for example, we'd get the right answer about 80% of the time. Once we refine the calls with those last 400 CPU months of compute power, we reduce that error rate from 20% to about 2%. So that's nice. There's a couple of other interesting things when you look at this type of data that are kind of fun to think about. So when we started the project, we had different groups who had their own analysis tools, and we were sort of set out this strategy where we said, we'll evaluate them, pick the best, that'll be our official answer for the project. So there was a team at the Broads, one here in Michigan, one at Sanger. And so we each analyzed the entire data set and made a set of calls. And then we went out to generate a truth set for a subset of those and evaluate. What you can see is that depending on what metric you choose, you end up with slightly different answers. So if you look at homozygous reference errors, well, the Broad here has the lowest rate by a hair. We're doing pretty well, and Sanger's doing a little bit less well. If you look at heterozygous errors, well, we're doing the best. Sanger's pretty close, and the Broad's clearly worse. And if you look at non-reference errors, Sanger's doing better, we're doing okay, and the Broad's the worst. And so obviously we looked at this and said, clearly the Michigan results are the best. That's what we should choose. But it was hard to get to a consensus across the entire project that was the right interpretation. And so after kind of many hung discussions, one of the bureaucrats in the project, we have some funders that join our calls and said, why don't you guys come up with a consensus? Why don't you have 3 answers, why don't you take a vote? If 2 of them agree, then you'll pick that one at each position. And, and to me, this seemed like a terrible solution, right? You have 2 bad methods, but they outvote the better method or something like that, right? But, because they were paying the bills, we said, we'll try it. And so that's the bottom row here. And it turns out that actually doing this kind of consensus approach greatly reduces the error rate. What's happening here, actually all the methods are not using all the information that's in the data because it's too complex. And so they each made different approximations and decisions. When you combine them, you do much better. It's the same thing when you look at things like predicting what a Netflix user wants to watch next. It turns out that you can use many sophisticated statistical models, make a prediction, and the best possible prediction is by running a few different models and letting them vote among themselves. So kind of cool, but it also says, hey, you actually don't want to just spend those 400 CPU months. You want to spend them a couple of times or something. OK, things that you get to see when you look at the data in the end. Here's a summary of genetic variation around transcripts. And so you see, for example, that there's a clear depletion when you are right on top of any gene, and that depletion actually extends for about 0.1 centimorgans, about 100 kilobases. So it's kind of nice to see some of these things that you'd predict, natural selection is occurring at the gene level, but actually quantifying how far from the gene it extends and so on. As the project has progressed, this was our pilot paper, we've added more individuals and discovered more variants. We're now at about 40 million. And one nice thing about these methods that borrow information across individuals, when you look at the error rates, we're also getting much more accurate at how we call each individual genotype. The most recent release, about a month ago, we actually integrated all different types of variation. We were analyzing the large deletions, the single site SNPs, and the indels into a set of chromosomes for each individual. And this data is used in many different kinds of disease studies. You can use it in resequencing experiments to screen out variants that are likely not to be disease-causing. If you are interested in fine mapping a region or studying it in detail, you can look up all the variation that's been seen in 1,000 individuals, design an array to inexpensively query it in your own samples. You could actually do try and connect the haplotypes we see here to haplotypes you've generated with lower resolution and fill in data by imputation in your own studies. So here's a different sequencing project, this one with disease samples. So here, two key collaborators are Francesco Cuca and David Schlesinger, so their names are there. And so what are we doing here? We have a population of about 6,000 individuals recruited from 4 towns in an isolated valley in Sardinia, which is an island off the coast of Italy. The total population of the valley is about 10,000. So we have about 60% of the people enrolled in the study. They come in for a medical exam every 3 years, and we phenotype them in detail. So we have a series of quantitative traits related to aging, ranging from things like blood pressure to cognition and so on. And we originally set out to sequence 1,000 individuals at least 2x coverage, which is quite low, but at the time was what we could do with our budget. And without having spent out our budget, we now have 1,700 individuals sequenced at almost 4x. So we have 4 times more data than planned already, and we're not done yet. So when we wrote the project, we assumed sequencing costs are going to go down by a factor of 2 every year. And the reviewers said, maybe that's a little bit aggressive, But in fact, they've gone down by a factor of 4, and so we have already quite a bit more data. One nice thing, they have a very nice team of hardworking people there in Sardinia, and I like to say that we print out the sequences in those pieces of paper, and then we manually align them and so on. So it's not quite true. Okay, so designing the study, how do you set up the details? How do you figure out who to sequence? So because we have pretty much the entire a large part of the population in this valley, we have lots of relatives. We can find many families that look like this, and we can make decisions about who to sequence. It turns out that if I sequence the 3 individuals at the top of that pedigree, the ones that are shaded, I actually am able to deduce the genomes of their relatives because it's effectively the same chromosomes that are moving through the family. And I'm going to also be able to deduce half of the genome for the bottom generation. And for in a relatively effective manner, I can add a few more people, sequence them, and be able to deduce the sequence for the entire family, getting me a further cost savings. So this is just to see, how sequencing is progressing. This has mostly been the work of a postdoc working with the Sequencing Corps here in Michigan. March 2010, when we started, we were getting about 5 gigabases of data for a fixed amount of cost, a fixed amount of effort. Now for the same amount of cost and effort, we're about 35 gigs. So when you see these things saying the throughput is increasing fourfold each year, it's really true, and it's kind of nice to watch. And what happens when you look at a particular trait and find out what you learn? So here's LDL cholesterol. So LDL cholesterol is an interesting trait because it's a very strong risk factor for heart disease. When we do a scan, here in red, you are the results of our previous scan based on a standard genotyping array, and in gray in the background are the results from a sequencing study. The sequencing study has a lot more markers. We're looking at 20 million markers instead of 2 million. Most of the results are concordant. So you see a big peak here at ApoE, another peak here at LDLR, PCSK9, SORT1, and ApoB are all genes that have been implicated for quite a while in LDL cholesterol metabolism in humans. And quite a while here means, in some cases just 2 or 3 years. But it turns out there's also a very strong peak here, which is a stop codon in the beta-globin gene that had been completely missed. It had been missed because this variant is unique to Sardinia, so it's not in these common variant arrays, and it's relatively rare. If you go and examine it in more detail, it turns out that this particular stop codon is the biggest determinant of LDL cholesterol levels in this population. It's associated with a large increase in turnover of red blood cells, and making these new red blood cells ends up consuming your cholesterol. So you have much lower cholesterol if you have this variant. And in heterozygotes, it appears to reduce your risk of heart disease and things like that. So it's kind of a nice story that we would have missed if we just used the standard technology. So it's kind of nice to see it coming up. Okay, so what I wanted to give you is a flavor that sequencing lets us do things we couldn't do before. Getting to sufficient sample sizes is still a challenge. We'd really like to sequence hundreds of thousands of individuals. Here we're talking about studies with low thousands. So we need to think very carefully about good designs, interesting samples. And I tried to give you a flavor of some of the challenges in analyzing the data, and it's at least as tough as generating it. And I think when people talk about, well, when the costs drop enough, you're going to have your genome sequence for a few $100s or maybe less. And on the current trajectory, the analysis might cost more than that. Okay, so these are the people in my group here in Michigan, key people here are Hayun, who does a lot of our sequence processing pipelines, Carlo, who did all the analysis for the Sardinia data, and Fabio, who actually generated most of it in the lab. So, all right, so thanks. So you see new variants in every genome. So the largest data set we have is an amalgamation of different sequencing projects where we have 12,000 individuals exome sequenced, and there more than half of the variants are seen in a single individual. And actually, there's interesting reasons to try and get them all, because say variants like stop codons, things that disable a gene, are extremely rare. But you could imagine that it would be great if we could have a catalog of where we have one person with a stop codon for every gene, because then if we want to know about the function of the gene, we could call that person back and do some tests on them. Well, to get to that, we will probably have to sequence well over 100,000 people deeply. So, so there's very interesting experiments that you can do if you can reach that kind of scale, and there's many variants that are rare and interesting. So, yeah.
What tool were you using?
Okay, what part of the analysis? Sorry.
Well, I'm wondering specifically like the haplotype analysis.
Okay, so for doing the haplotype sharing-based calling, we use a tool that we developed here called MAC, and it basically, uses hidden Markov models to search for shared haplotypes among large sets of individuals. The upstream steps are using things like BWA and SAMtools and GATK, and a combination of them most often. All right, so I think I should.
Any other questions? Thank you. That was fantastic. Look at this factoid about the Nature paper is like stunning. Let's all, our hats off to you. This is absolutely great. And as far as the investments, we're doing significant investments to enhance the cyber infrastructure at an enterprise level to allow for us to grow a DNA biolibrary to 100,000 specimens, annotated with health record, safe and secure and private to anticipate the HIPAA ruling that's probably going to come down the pipe, and we're really proud to be working with them.
I mean, you can only do this in a place like Michigan. It takes lots of different people to publish it.
I was telling Jim that yesterday in my meeting with Ted Hans and Dr. DeWitt, who's our CIO on the health system side, that it wasn't the 40 million for the sequencing, but it was at least 5 or 10 million to get some of the infrastructure in place to help you. And we really are working hard to get this working in the institution. Okay, we've got our final speaker up here.
Well, I'd like to thank the organizers for giving me the opportunity to share my excitement about the power of genomics and bioinformatics in modern biology. And I want to tell you a little bit about research of my lab, which is it's going to be very different from what you just heard. So I will start with a brief background about our research questions, and I will tell you about one specific genomic project that's going on in the lab right now, and I will tell you a little bit more about the tools we use and bioinformatic approaches we try to apply in the lab. I will tell you very briefly about findings of our research so far, and I want to finish with a take-home message about bioinformatics here at U of M from a biologist perspective. Well, I'm assuming that everyone knows what the genome is, and that the human genome has been sequenced over 10 years ago. And it wasn't the first genome to be sequenced. There were bacterial genomes and the yeast genome sequenced earlier. And right now we have probably thousands of various organisms with sequenced genomes. So everyone thought, wow, great. We'll know the sequence of the human genome. We'll know everything about human. And 10 years later, that's a pretty big disappointment. So the sequence of the genome is huge, is cryptic, and we have no clue what it means. And it's a really big challenge to really understand what the genome is doing, how the genome is regulated, and how life translates information from the sequence of nucleotides in DNA to us or to other organisms. So the big goal of the big part of biology, including my lab, is to understand how the genomes work. And probably one of the reasons why I was asked to be here is to show you that biology is not only human, it's not only biomedical research, and that's true. So I'm doing my research on plants, and in general, model systems and plants specifically are really convenient. There is a lot of questions which are very hard to ask in the human system for practical reasons, for ethical reasons, and in the model systems we can ask them really easily. So plants, even though many of you who are in the biomedical field are not really so excited about plants, plants are actually really good models for biomedical science, because plants are eukaryotic and they are multicellular. So plants share pretty much majority of the basic mechanisms with human and with vertebrates. At the same time, they are much easier to work with than animals. A lot of practical and ethical and other concerns are really not a factor. Although plants have their own specificity, there has been specific fields where basic research has been done in plants much more effectively than in other systems. At the same time, plants are really exciting on their own. They are the major harvesters of energy, so they are critical for this world. And they do a lot of really fascinating stuff, and I shouldn't even start talking about this. So the specific question we are asking about the genomes is how non-coding RNA regulates activity of the genomes. So let me introduce you real quick to the non-coding RNA. So the very basic fact about life, and something I usually teach in one of my first genetics lectures, the information in living organisms flows from the genome, which is DNA, to proteins, and proteins perform the actual function. So they build our bodies, they are enzymes, and they actually do stuff. But there is an intermediate, and this intermediate is called RNA. It's also a nucleic acid. It's very similar to DNA. It's only one atom being different between nucleotides in DNA and RNA. And there are many reasons why this intermediate is needed. And for years, people thought that RNA is just an intermediate. However, it turned out that there is a whole lot of RNAs which are not intermediates. They are doing something else. And some of them have been known for years now. And the research of the genomic era made people realize that actually the majority of the genome may be encoding RNA, which are not encoding proteins. So these are the non-coding RNAs. And trying to understand what they are doing is the specific goal of my lab. So let me shift to even more specifics and tell you about the specific project in the lab. And this is the project where we successfully used a genomic approach, and we learned a lot of stuff in the process of working on this project. So we want to understand what a specific class of non-coding RNA is doing on the genome-wide scale. And it is important because there has been a lot of research on various regulatory proteins and RNAs, which would study only specific fragments of the genome. And people really love to generalize. Okay, we found these 2 genes which are regulated by this non-coding RNA, so it means that this non-coding RNA is doing whatever it's doing on the whole genome. But it wasn't really supported by any data. So that's why the genomic approach is really important to allow us to make general conclusions about functions of various factors. So we try to study a class of non-coding RNA by studying a protein, which we knew already before, that binds to this non-coding RNA. And we knew that this non-coding RNA is guiding the protein to DNA. And this protein is called Argonaute. It is involved in controlling activity of various areas of the genome. So what we wanted to do, we wanted to find where this Argonaute protein binds in the genome, and we wanted to use this information to understand what is non-coding RNA doing, and hopefully also understand how exactly it is working. And to achieve this goal, we performed a ChIP-seq experiment, and there is a lot of words on this slide, and oh, you can see the very top. But it's in principle a very simple method. What we did, so what we are doing, we are grinding plants in liquid nitrogen, extracting proteins, and then we are purifying our protein of interest. In this case, it is the Argonaute protein. And when we purify the protein, associated DNA is co-purified. So if the protein binds to a specific region of DNA, if we purify the protein, we'll also purify DNA of this specific sequence. So we can get this DNA and sequence it using next-generation sequencing, which allows us to get nowadays 10 million of reads per every experiment. And having this data, we have to analyze it to understand what is the function of the protein. So let me tell you real quick about the way we analyze the data, and then I will show you a small sample, and then I will tell you a little bit more about the tools we actually use to analyze the data. So we always have to start with mapping the sequencing reads to the genome. And once we map them to the genome, we can look at the specific fragments of the DNA. And if we see a lot of reads mapping to this region, more than in our control, we can say that our Argonaute protein binds to this specific part of the genome. The next step is to visualize it somehow. And I will show you an example of visualization in a moment. We don't have to find significant effects, so distinguish what is random from what is a biologically significant binding of the protein. And then we have to do something which I called creative analysis or a downstream analysis. So basically start with this enormous data set and then do some magic and end up with understanding. And I will tell you a little bit more about this last part in a moment. So a really important step is to visualize the data. And this is an example how it looks. And you can see that this is a fragment of the Arabidopsis chromosome. And here on top are genes. This is one gene. This is the second gene. And here, well, this part up here comes from different sets of experiments. So let's just forget about this top part right now. And these three lanes come from our Argonaute 4 ChIP-seq experiment. So, and this is our experimental lane, and this is a negative control. So you can see over here that there are some sequencing reads aligning, but they are in both in our experiment and in the control. So there is no significant binding here. But in this region here, there is a lot of reads aligning in our experimental line, but much less in the negative control. So we can say that this part of the genome is associated with our Argonaute protein. Okay, so let me tell you real quick about the tools we use. And so the first step, mapping to the genome, it's pretty routine. And in our application, we just have a simple Linux workstation, and because Arabidopsis genome is kind of smaller than the human, not much smaller, but it is smaller, we can just map it. It takes a few hours to map a pretty large experiment to the genome. And the software is pretty standard, so that is not a big challenge. Then to visualize, what we need is a web server. And it's actually not so easy to get a web server up and running for many reasons. But most visualization software operates as web servers for us to be able to use it first, but then after the data are published, to make it available to the community that other people can browse through our data and use it. The next step, finding significant effects, or we call it that it's peak calling, also uses just a simple Linux workstation. However, the software is usually kind of specialized because there's a ton of various peak calling methods, and our experiments are usually not something really standard. So in practice, what we have to do is to dig through the literature, find like 10 or 15 various algorithms, try them all with various parameters, design smart controls, and using those controls, decide which approach works best. And the final step, trying to convert this data set into understanding, this is actually the core, the main challenge and the most exciting part. And it doesn't really take much of computing power. We still use our Linux workstation, although I could easily do it all on my laptop, which I use for this presentation. And there is a bunch of specialized software, and we also have to write scripts and small pieces of software on our own. And the general approach we take is we look at the visualized data, look through the genome, and try to make observations. And let me just give you an example. For instance, you may see that this binding region is aligned pretty well with start of a gene. And that's something we actually observed over several genes. So we hypothesize, okay, Argonaute 4 binding is correlated with starting points of genes. And now we have to move on and test it on a genome-wide scale. So take all genes from the whole genome and look if there is Argonaute 4 binding on all of them. And to do it, if we are lucky, we find a specialized piece of software online. If we are unlucky, we don't find it, we have to write it, which is usually not really difficult, even for a dumb biologist. Well, try to get our answer and try to design a control to make sure that our answer is not wrong and our software has no bugs, and everything fits into a story. Let me tell you real quick about our conclusions, which I'm really super excited about, and I'm afraid that I wasn't able to give you sufficient background to make you the same excited, but hopefully at least you'll understand at least a little bit of my excitement. So we were able to find where non-coding RNA is guiding this Argonaute protein, and it turned out to be a very different part of the genome than what was expected. And those of you who heard about Argonautes know that this protein is involved in gene silencing, so the expectation was to see it on the silent part of the genomes, and there are huge areas of the genomes which are permanently turned off, and we're expecting to see this Argonaute protein on those huge inactive areas of the genomes. But we don't see it there. We see it exactly in places like here, in gene promoters. And promoters are very important pieces of genes. These are decision makers. These are fragments of DNA which decide when and where a specific gene is turned on and turned off. And to maybe make the point even stronger, the pattern of gene expression is in many cases much more important than the protein which is encoded. And for instance, comparing human to monkeys, the protein coding part of the genome is extremely similar. And many people think that it's the pattern of gene expression, so when and where the genes are expressed, that actually makes the difference between human and monkey. And so that's why we are very excited to see this Argonaute 4 protein and non-coding RNA function specific on gene promoters. And well, our hypothesis is that this non-coding RNA we are studying is specifically targeting promoters of a pretty large number of genes. This is like in the 500 to 1,000 range. So the large number of genes and is some kind of regulatory mechanism which affects transcription of those genes. And our very preliminary data suggests that it may be actually involved in stress response. That the genes which are targeted by Argonaute 4 and non-coding RNA seem to be, most of them seem to be regulated by stress, and we think that this Argonaute protein may be actually involved in stress response. Okay, so let me finish with a take-home message about our experience at this university, and because I hope that in this room there may be some decision makers who may make our life easier for the future. It's really remarkable that nowadays computers became standard research tools, like a pipetter, like a centrifuge. We also have a computer in the lab, and all we really need, except winning with our with biological dampness and our difficulties in writing software and understanding bioinformatics. The other thing we need is flexibility. So we need to be able to try as many tools as possible, and we need to be able to follow evolving bioinformatic tools. And it takes installing new software 3 times a day. It takes doing, well, whatever idea we have now, we want it done 2 hours from now. And unfortunately, this is probably very specific from unit to unit, but this university has a lot of regulations about computers. And it happened to us several times that we wanted to do something, and we heard, no, you can't do it. This flexibility is really important to use computers for research efficiently, especially for research like ours, which takes a lot of trial and error and a lot of new tools being tested and developed all the time. And I think it's important for the administration of the university to understand that every limitation, and so every time someone takes a piece of this flexibility away, research, it interferes with research. And every time a piece of this flexibility is taken away, competitiveness of our university is also reduced. So I really hope that the university is going to invest in cyber infrastructure not only by building new supercomputers, but also by helping us being able to do whatever we need to do. All right, so let me finish with thanking members of my lab, especially Jordan, who did most of the work I was showing today, and other present and past members of my lab, and our great collaborators, Brian Gregory and Chi Zhang at UPenn. And thank you for your attention, and if there are any questions, I'll be happy to answer.
Great, thanks. Any questions? I did see some information technology professionals nodding their head. I guess one thing I would like to say is that sometimes the administration stands in the middle between the government and the faculty, and we are being barraged by compliance and regulatory issues right now, and we're doing everything in our power to try to understand those issues, hopefully limit the amount of red tape, and at the same time increasing the flexibility. That's our commitment. Question? The recording itself. Oh, okay, good. See, I missed the microphone.
So if you could identify maybe a key bottleneck for you, what flexibility don't you have that you would like to have? And is that something that maybe as a community we can help you achieve?
Actually, the biggest bottleneck has been resolved, and the breakthrough was when we got our own workstation and we convinced our departmental IT to get us the root password. And at that day, everything, well, almost everything has been solved. But they made a big exception for us by giving us the password. It's something they generally don't allow. Okay.
I think we have an opportunity to learn from you. There's a big biomedical focus to a lot of the computing that is being discussed here. And you're coming from campus side and biological focus. And so, from your perspective, what I'd like you to do is, kind of, give us some feedback on this difference and, what we can do to maybe bridge the gap between the biology and the campus side and the health.
Yeah, so actually that is a very good point, and I think that our university is kind of strong about it. And I have had experience from a different institution where I was a postdoc, and when I was emailing the sequencing core, if there was the word planned anywhere in the email would never get a response. And here I am getting responses from the sequencing core, even if I write planned, even if it's in the subject of the email. Well, I think it's important. It's really important for the biology part to really be on top and do really a breakthrough research, do stuff that's interesting enough to interest the biomedical folks as well.
Great, thanks. It's been a fantastic session. I want to thank everybody who's been fantastic here. And let's